Hello, dear travelers of the night. Welcome back to the Midnight Explorer, where we wander through the shadows of history, science, and wonder as the world sleeps around us. Tonight, I want to tell you a story. Not a simple story, but a tale that stretches across billions of years and trillions of miles. A story about darkness. Not the darkness we fear, but the darkness that holds everything together. The darkness that, paradoxically, creates the light. Settle in. Pull your blankets close. Dim the lights. Because tonight, we're going to explore something that has haunted humanity's dreams and driven our greatest minds to the edge of understanding. Tonight, we're going to discover the dark side of the Milky Way Galaxy. Are you ready? Then close your eyes for just a moment and let me paint you a picture. If you will, a child lying in a field somewhere on Earth. It doesn't matter when, it doesn't matter where. Perhaps it's thousands of years ago in ancient Mesopotamia. Perhaps it's last summer in your own backyard. Time collapses when we look up at the night sky, doesn't it? This child, let's call them Alex, a name that belongs to no particular time or place, lies on their back in the grass. The blades tickle the back of their neck. The earth beneath them still holds the warmth of the day radiating gently through their clothes. Above them, the sky has transformed. Where once there was blue, now there is black. But it's not truly black, is it? It's a rich, deep indigo, scattered with pinpricks of light. And there, stretching across the entire dome of heaven like a river of light, is something that takes Alex's breath away. A band of light. Cloudy, mysterious, shimmering. The Milky Way. Alex doesn't know what it is. No one in their village really does. The elders have stories, of course. Some say it's the road that souls take to the afterlife. Others say it's milk spilled by a goddess. Still others claim it's a bridge built by the gods themselves, connecting heaven and earth. But Alex, in this moment, knows something deeper. They feel it in their bones, in the quiet of their heart. That band of light is calling to them. It's whispering secrets in a language older than words. What Alex doesn't know, what they can't know, is that they're looking at their home from the inside. They're a passenger on a cosmic ship so vast that the human mind cannot truly comprehend it. They're one of hundreds of billions of souls living and dying on a tiny blue marble orbiting an average star somewhere in the suburbs of a galaxy that contains more stars than there are grains of sand on all the beaches of Earth. And most of what they're seeing, most of what makes that beautiful river of light possible, is invisible. It's dark. The ancient seekers. Let's travel now, you and I, through time. Keep your eyes closed and feel the centuries rush past like wind through autumn leaves. We're moving backward now, past the invention of the telescope, past the Renaissance, past the fall of Rome and the glory of Greece. We're going back, back, back to when humanity was young and the stars were our only teachers. Stop. We're in ancient Babylon, around 3000 BCE. Here, in the cradle of civilization, priests climbed to the tops of ziggurats, those great stepped pyramids that reached toward heaven. They climb at night, when the desert air is cool and the stars burn with a clarity that modern city dwellers will never know. These priests are not just religious figures. They are astronomers, mathematicians, timekeepers. They study the sky with a devotion that borders on worship, because to them the sky is not separate from the divine, it is the divine, writing its messages in light and motion. They name it. Every culture names it. In Sanskrit, it's Akasha Ganga, the river of heaven. In Chinese, it's Tianhe, the silver river. The Greeks will eventually call it Galaxias Kyklos, the Milky Circle, from which we get our word galaxy. But here's the thing that makes my heart ache with wonder. Despite their different names and stories, every culture that looks up at the night sky and sees that river of light feels the same thing. Awe, wonder, a sense of smallness that somehow doesn't diminish them, but elevates them. They're part of something vast. They're connected to something eternal. And they're right. Now, those ancient astronomers, brilliant as they were, couldn't see everything. They noticed the dark patches in the Milky Way, those regions where the river of light seemed to thin out or disappear entirely. What were these dark patches? Some thought they were holes in the celestial sphere, places where you could see through to the void beyond. Others thought they were clouds blocking the light. Still others believed they were the shadows of the gods themselves, cast across the heavens. They were all wrong. And yet, they were all, in a way, right. Imagine you're standing in a forest, a thick, old-growth forest where the trees tower hundreds of feet above you. Their branches interweave so densely that the sunlight can barely penetrate. You look up and you see patches of sky between the leaves, bright spots of blue, but mostly you see darkness. The canopy blocks your view. Now imagine you're not standing on the ground looking up. Imagine you're somehow suspended in the middle of the forest, surrounded by trees in every direction. Looking one way, you see many trees, their trunks overlapping in your field of vision, creating a wall of wood. Looking another way, you see fewer trees. Perhaps you're looking along a gap or clearing. The forest seems less dense in that direction. The Milky Way is like that forest. We're not standing outside it, looking in. We're in the middle of it, and when we look towards the center of our galaxy, towards the densest part of the forest, we see more stars, more light. The Milky Way appears brighter and thicker in that direction. When we look towards the edge, we see fewer stars. The Milky Way appears fainter. And those dark patches? That's where there's dust. Cosmic dust, clouds of gas and dust so thick that they block the light of the stars behind them. But here's the thing that would take humanity thousands of years to understand. Those dark regions aren't empty. They're not holes in the heavens. They're not nothing. In fact, they're pregnant with something. They're wombs. They're the birthplaces of stars. The darkness, it turns out, is where the light begins.
Let's jump forward now to the 10th century CE, where in Persia, in the Islamic Golden Age, when the torch of learning burned bright in the East while Europe slumbered in its dark ages. Here, we meet a man named Abdal-Rahman al-Sufi. He's an astronomer, one of the greatest of his age. He's created a book called The Book of Fixed Stars, cataloging everything he can see in the night sky. Al-Sufi looks at the Milky Way with careful, trained eyes. He documents its shape, its brightness, its structure. But he also notices something else, something that his predecessors might have seen but didn't document. There's a small, faint, cloudy patch in the constellation of Andromeda. It doesn't move like a comet. It doesn't change like a planet. It's just there, a little smudge of light. He calls it the little cloud. What Al-Sufi has seen, though he doesn't know it, is another galaxy entirely, the Andromeda Galaxy, our nearest large galactic neighbor, over 2 million light-years away. He's seeing the light of 1 trillion stars, so distant that they blur together into a single faint glow. Think about that for a moment. In the 10th century CE, a man in Persia looked up at the night sky and recorded something so distant that its light had been traveling toward him for more than 2 million years. When that light began its journey, humans didn't exist. Our ancestors were still learning to walk upright on the plains of Africa. And that light, traveling at 186,000 miles per second, the fastest thing in the universe, still took 2 million years to reach his eyes. The universe, we're beginning to understand, is not just big, it's not just vast, it's something for which we don't have adequate words. It's a depth of space and time that breaks our intuition, shatters our sense of scale. And most of it, most of the universe, we can't even see. It's dark. It's January 1610. We're in Padua, Italy, in a cold room at the top of a house. A man stands by a window, shivering slightly, holding something in his hands. His name is Galileo Galilei. He's 45 years old, and he's holding a tube made of leather and wood with lenses at each end. A telescope, though the word is so new it barely exists yet. Galileo didn't invent the telescope. That honor belongs to Dutch spectacle makers, but Galileo has improved it, refined it, turned it into something powerful enough to see what no human has ever seen before. Tonight, he points it at Jupiter and sees 4 moons orbiting the planet, a miniature solar system that will change forever how we understand our place in the cosmos. But that's not the discovery that matters most to our story. A few nights later, Galileo turns his telescope toward the Milky Way, and he sees something that makes him gasp. He sees something that he will later write about with barely contained excitement. The Milky Way, that cloudy band of light, is not cloudy at all. It's made of stars, thousands of them, tens of thousands, packed so closely together that to the naked eye they blur together into a continuous glow. But through the telescope, even his crude, primitive telescope, they separate. They resolve. They become individual points of light, each one a sun, perhaps with its own worlds, its own stories. Imagine being Galileo in that moment. Imagine being the first human being in all of history to know this truth. The Milky Way isn't a cloud. It isn't milk spilled by the gods. It's stars, more stars than you could count in a lifetime, all crowded together, all shining, all burning with the same nuclear fire that powers our sun. But Galileo, brilliant as he is, doesn't understand the full implication of what he's seeing. He thinks the stars are all roughly the same distance from Earth, fixed to a celestial sphere. He doesn't realize that the Milky Way is a structure, a vast rotating disk of stars bound together by gravity, with our sun as just one member of this cosmic family. That understanding will come later, much later. Time passes, a century, 2 centuries. The telescope improves, astronomers multiply, they're scattered across Europe, each one mapping the sky, cataloging stars, trying to understand the architecture of the heavens. One of these astronomers is William Herschel, a German-born musician who fell in love with the stars and built the largest telescopes in the world in his backyard in England. The year is 1785. Herschel has an ambitious idea. He wants to map the Milky Way. He wants to count the stars in different directions and use those counts to determine the shape of the galaxy. It's brilliant in its simplicity. If you're inside a forest, you can figure out the shape of the forest by counting how many trees you see in different directions. More trees in one direction means the forest extends farther that way. So Herschel counts. Night after night, month after month, he and his sister Carolyn point their massive telescope at different parts of the sky and count stars. They count until their eyes water. They count until they can barely see straight. And slowly, a picture emerges. The Milky Way, Herschel realizes, is disc-shaped, flat and wide, like a coin or a wheel. Our sun sits somewhere in the middle of this disk. When we look toward the edge of the disk, perpendicular to its plane, we see fewer stars. When we look along the plane of the disk, we see many more stars, which is why the Milky Way appears as a band around the sky. It's a triumph of observational astronomy. Herschel has, for the first time, given us a three-dimensional picture of our galaxy. But there's a problem. There's something Herschel doesn't know, something that won't be discovered for more than a century. There's something between the stars, something that blocks light, something dark.
Imagine you're trying to map a city from inside the city, but it's a foggy day. You can see buildings nearby clearly, but the ones farther away grow dim and hazy. Eventually, they disappear entirely into the fog. If you didn't know about fog, you might think the city just ended, that there were no more buildings beyond what you could see. This is what happened to Herschel, and to generations of astronomers after him. The space between the stars isn't empty. It's filled with gas and dust, the remnants of dead stars, the raw material of stars yet to be born. This dust is incredibly thin, far thinner than any vacuum we can create on Earth. But space is so vast that even this thin dust adds up. Over thousands of light years, the dust accumulates. It absorbs light, especially blue light. It makes distant stars appear dimmer and redder than they really are. It creates those dark patches in the Milky Way that the ancients noticed, not because there are no stars there, but because the dust is so thick it blocks our view entirely. For centuries, astronomers looked at the Milky Way and drew their maps, not realizing they were looking through a veil. They were like artists painting a landscape through dirty glass, unknowingly distorting everything they saw. This dust had consequences, profound consequences for our understanding of the universe. It made us think our galaxy was smaller than it really is. It made us think our sun was near the center, when really we're far out in the galactic suburbs. Most importantly, it hid from us the true scale of the darkness. Let's move forward again, to April 26, 1920. We're in Washington, D.C., at the Smithsonian Museum of Natural History. Two astronomers are about to engage in what will become known as the Great Debate, one of the most important scientific discussions of the 20th century. On one side is Harlow Shapley, a young, brilliant astronomer who has just remapped the Milky Way using a new technique. He's discovered that our galaxy is much larger than anyone thought, about 300,000 light-years across. He's also discovered that our sun is not at the center of the galaxy, but far out in the outskirts, about 50,000 light-years from the true center. Shapley believes the Milky Way is the universe. Everything that exists, he thinks, is contained within our galaxy. Those fuzzy spiral nebulae that telescopes have been finding, they're just gas clouds within our own Milky Way. The universe is one galaxy, and that galaxy is ours. On the other side is Heber Curtis. He believes something radical. He believes those spiral nebulae are island universes, galaxies in their own right, separate from and comparable to our own Milky Way. He believes the universe contains not one galaxy, but many, perhaps millions, perhaps billions. The debate is civilized, scholarly, but underneath the polite language there's something primal at stake. The question being asked is one that echoes through all of human history.
How big is the universe, and where do we fit in? The irony, beautiful and sad, is that both men are partly right and partly wrong. Shapley is right that the Milky Way is enormous, and that we're not at its center. But he's wrong about the nature of spiral nebulae. Curtis is right that spiral nebulae are distant galaxies, but he's wrong about the size of our own Milky Way. His measurements are too small by a factor of 3. The truth, as is so often the case, lies somewhere in between. But to find that truth, we need someone new, someone with access to the most powerful telescope in the world. Before we get to that someone, we need to make a detour. We need to talk about someone who doesn't appear in the great debate, someone whose name wasn't on the stage that day, but whose work made everything possible. Her name is Henrietta Swan Leavitt. It's 1908. We're at Harvard College Observatory, but we're not in the telescope dome. We're in a building nearby, a crowded room filled with women working at desks, examining photographic plates, glass images of the night sky, captured by telescopes and then mailed to Harvard for analysis. These women are called computers, human computers, calculating and cataloging the stars. They're paid less than male astronomers, given no recognition, no authorship on papers. They're expected to do tedious work, measuring the brightness of stars, classifying them, creating catalogs. One of these women is Henrietta Leavitt. She's deaf, having lost most of her hearing to an illness. She works in silence, which in a way seems fitting, given that she's studying objects so distant that no sound from them could ever reach Earth. Leavitt is examining stars in the Small Magellanic Cloud, a dwarf galaxy visible from the southern hemisphere, a satellite of our Milky Way. She's looking at a type of star called the Cepheid variable, stars that pulse, getting brighter and dimmer in a regular rhythm, like cosmic heartbeats. And she notices something that will change everything. The brighter a Cepheid variable is, the longer its pulse period. There's a relationship, a law, connecting how bright these stars really are to how fast they pulse. Think about what this means. If you know the period of a Cepheid's pulse, you know its true brightness. And if you know its true brightness, and you measure how bright it appears from Earth, you can calculate how far away it is. Henrietta Leavitt has discovered a cosmic yardstick, a way to measure distances to the stars. She publishes her findings in 1912. She receives almost no recognition in her lifetime. She dies young of cancer in 1921, at the age of 53. But her discovery, her gift to humanity, will be used by others to unlock the true scale of the universe. It's October 1923. We're on top of Mount Wilson, high above Los Angeles. The air is thin and cold. The sky is achingly clear, filled with stars that don't twinkle. The steadiness of the view at high altitude makes them seem frozen, like jewels on black velvet. Inside the dome of the 100-inch Hooker telescope, the largest in the world, a man sits at the observer's cage, eye pressed to the eyepiece, hand gently guiding the massive instrument. His name is Edwin Hubble. He's 34 years old, a lawyer turned astronomer, tall and athletic, with a confidence that some find charming and others find arrogant. Tonight, Hubble is photographing the Andromeda Nebula, that same fuzzy patch that Al-Sufi noticed 1,000 years ago. Hubble's been photographing it for months, taking image after image, looking for novae, stars that suddenly brighten and then fade. He develops the photographic plate in the darkroom, and there, in the outer edge of Andromeda, he sees it, a star that wasn't there before, a nova. Or is it? He compares it to previous images. The star appears in some, disappears in others. Its brightness changes. It's not a nova. It's something better. It's a Cepheid variable. Hubble's heart races. He knows what this means. He knows Henrietta Leavitt's law.
He can measure the period of this Cepheid. He can calculate its true brightness. He can determine how far away it is. He does the math. The numbers are staggering. The Andromeda Nebula is 900,000 light-years away. Later measurements will revise this to 2.5 million light-years, but even Hubble's initial estimate is revolutionary. It's far beyond the Milky Way. It's not part of our galaxy at all. It's its own galaxy, a vast collection of hundreds of billions of stars, so distant that all those stars blur together into a single faint glow. Curtis was right. The spiral nebula are island universes. The universe is not one galaxy. It's billions of galaxies scattered through space like stars in the night sky. Each one a collection of billions of stars, each one separated from its neighbors by millions of light years of darkness. The universe, suddenly, has become vastly larger than anyone imagined. And most of the space between the galaxies, is dark, empty, void. Or is it? We're going to jump ahead now. It's 1933. We're in California, at the California Institute of Technology. A Swiss astronomer named Fritz Zwicky is studying clusters of galaxies, groups of galaxies bound together by gravity, orbiting around their common center of mass. Zwicky is measuring how fast these galaxies are moving. And he's noticing something strange, something that doesn't make sense. The galaxies are moving too fast. Let me explain. When objects orbit around each other, like planets around the sun, or stars in a galaxy, or galaxies in a cluster, their orbital speed depends on gravity. The more mass there is in the center, the faster the outer objects have to move to avoid flying apart. Zwicky calculates how much mass these galaxy clusters should have based on the visible stars. Then he measures how fast the galaxies are actually moving. The numbers don't match. Not even close. The galaxies are moving so fast that they should be flying apart, escaping from the cluster entirely. The visible mass isn't enough to hold them together. There should be more mass, a lot more mass, but Zwicky can't see it. He proposes something radical. He proposes that there's invisible matter in the universe, matter that doesn't emit light, doesn't absorb light, doesn't interact with light at all. Matter that we can only detect through its gravitational effects. He calls it Dunkelmaterie, dark matter. His colleagues think he's crazy. They dismiss his ideas. Dark matter becomes a curiosity, a footnote, something to be ignored. But Zwicky is right. He's seeing evidence of something that will revolutionize our understanding of the universe. He's seeing the shadow of the dark side. Let's move forward again. It's the 1970s. We're in Washington, D.C., at the Carnegie Institution. A woman sits at her desk surrounded by data, charts and graphs showing the rotation speeds of stars and spiral galaxies. Her name is Vera Rubin. She's an astronomer who has fought for decades to be taken seriously in a field dominated by men. She's been denied access to telescopes because of her gender. She's been overlooked for positions and honors, but she's persisted, driven by curiosity and a stubborn refusal to give up. Now, in her 40s, Rubin is doing something that seems simple, but is actually profound. She's measuring how fast stars rotate around the centers of their galaxies. Here's what should happen based on everything we know about physics. Stars near the center of a galaxy, where most of the visible mass is concentrated, should orbit quickly. Stars farther out, where there's less mass, should orbit slowly. Just like planets in our solar system. Mercury zips around the sun every 88 days, while distant Neptune takes 165 years. But that's not what Rubin sees. Instead, she sees that stars far from the galactic center
are orbiting just as fast as stars near the galactic center. The rotation curve, as astronomers call it, is flat. This shouldn't be possible unless there's more mass than we can see. Unless galaxies are embedded in vast halos of invisible matter, matter that extends far beyond the visible edge of the galaxy, matter that doesn't glow, doesn't shine, doesn't interact with light at all. But it's there, making up 85% of the galaxy's mass. The stars are the garnish. The dark matter is the main course. Our Milky Way, our home galaxy, is the same. We live in a galaxy that's mostly invisible. We're floating in darkness, surrounded by it, held together by it. Now we come to one of the deepest mysteries in all of science. A question that has haunted physicists for decades, that drives experiments deep underground and in orbit around Earth, that may be the key to understanding the fundamental nature of reality. What is dark matter? Let's be clear about what it isn't. It's not just regular matter that happens to be dark. It's not black holes or brown dwarfs or planets or dust clouds. We've looked for all of those things, calculated how much of the universe's mass they could account for. They're not nearly enough. Dark matter is something else. Something exotic. Something that doesn't fit into our current understanding of physics. Here's what we know. Dark matter doesn't emit light, or absorb light, or reflect light. It doesn't interact with electromagnetic radiation at all. The only way we know it exists is through gravity, through its effect on the motion of stars and galaxies, through its bending of light from distant objects. It's like a ghost. It passes through normal matter almost without interacting. Right now, as you listen to this, trillions of dark matter particles are passing through your body, through the Earth itself, without touching a single atom. They're streaming through everything, invisible, intangible, yet undeniably present. Scientists have proposed many candidates for what dark matter might be. WIMPs, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. Each hypothesis leads to experiments, to detectors buried deep underground or sent into space, trying to catch just one interaction, one collision between a dark matter particle and a normal atom. So far, we've found nothing. The darkness keeps its secrets. Now, let's turn our attention to the center of our galaxy, that bright, dense core that ancient astronomers marveled at. What lies there, at the heart of the Milky Way? For a long time, we couldn't see. Remember that dust we talked about, the stuff that blocks visible light? There's a lot of it between us and the galactic center. Looking at the center of the Milky Way in visible light is like trying to see through a wall. It's impossible. But in the 1930s, a young engineer named Carl Jansky built an antenna to study radio interference for Bell Labs. He was trying to figure out what was causing static in transatlantic phone calls. He found something unexpected: radio waves from space. And some of the strongest signals were coming from the direction of the galactic center. Radio waves, unlike visible light, can pass through dust. They give us a new way to see, a new set of eyes. Over the decades, as radio astronomy developed, we began to build a picture of the galactic center. It was strange, violent, hot gas, magnetic fields, something generating enormous amounts of energy. Then, in the 1970s, astronomers discovered an intense source of radio waves right at the very center of the galaxy. They called it Sagittarius A star, pronounced Sagittarius A star. What was it? To answer that question, we need to fast forward to the 1990s and 2000s. Two teams of astronomers, one led by Andrea Ghez at UCLA, another led by Reinhard Genzel in Germany, begin a long-term project. They're going to watch the stars near the galactic center, not just for a few nights, but for years, decades. They're going to track the motion of individual stars, map their orbits, see where they go and how fast they move. This requires extraordinary patience and extraordinary precision. The galactic center is 26,000 light-years away. The stars there appear so close together that they can barely be distinguished even with the best telescopes. It's like trying to track individual fireflies from miles away when they're all swarming around the same spot. But Ghez and Genzel persist. Year after year, they collect data. They watch as stars trace out orbits around something invisible, something at the very center where Sagittarius A star sits. One star in particular catches their attention. It's called S2, and it has the shortest orbital period of any star they can track. It whips around the galactic center once every 16 years, moving at speeds up to 3% of the speed of light. That's about 11 million miles per hour. From its orbit, they can calculate the mass of whatever it's orbiting. 4 million times the mass of the Sun, contained in a region smaller than our solar system. There's only one thing it can be. At the heart of our galaxy, at the heart of every large galaxy in the universe, there sits a black hole. Not the relatively small black holes, formed when massive stars explode, but monsters, millions or billions times more massive than the Sun. These are the darkest objects in the universe. Not dark because they don't produce light, but because their gravity is so strong that even light cannot escape. They're holes in the fabric of space-time itself, regions where the laws of physics as we know them break down. On April 10, 2019, humanity achieved something remarkable, something that would have seemed impossible just a generation earlier. We took a picture of a black hole. Not our black hole. Sagittarius A** is difficult to image because it varies rapidly and is surrounded by material that moves and changes. Instead, we imaged the supermassive black hole at the center of a galaxy called M87, 55 million light-years away. The image was captured by the Event Horizon Telescope. Not a single telescope, but a network of radio telescopes scattered across the Earth, from Hawaii to Chile to Antarctica. By combining their signals, they created a virtual telescope as large as the Earth itself. And what did they see? A ring. A glowing ring of hot gas being accelerated to nearly the speed of light as it spirals into the black hole. In the center, a dark circle. Not the black hole itself, but its shadow, the region where light is so bent by gravity that it cannot escape. The image is grainy, imperfect, but it's also profound. For the first time, we're seeing the shadow of something that cannot be seen. We're seeing darkness defined by light, absence defined by presence. In 2022, the team released a similar image of Sagittarius A*, our own galactic center, our own heart of darkness. It looks similar to M87's black hole, but smaller, more active, surrounded by swirling material that flickers and changes on timescales of minutes. This is what sits at the center of the Milky Way. This is the anchor point around which hundreds of billions of stars, including our Sun, orbit. A point of such extreme darkness that it defines, in many ways, the shape and evolution of our entire galaxy. Let's pull back now. Let's zoom out from our galaxy. Out past our nearest galaxies, out past our local group, out past the Virgo supercluster. Let's look at the universe on the largest scales imaginable. What do we see? For most of the 20th century, astronomers assumed that galaxies were scattered randomly through space, like stars scattered across the night sky. But as they began to map more and more galaxies, measuring their distances and positions, a pattern emerged. Galaxies aren't randomly distributed. They're organized. They form structures, chains, sheets, filaments, all connected together in a vast cosmic web. And between these filaments, voids. Enormous, empty regions, hundreds of millions of light-years across, containing almost no galaxies at all. It's like looking at foam. The galaxies cluster on the surfaces of giant bubbles, while the interiors of the bubbles are nearly empty. It's like the structure of a brain, with neurons connected by axons and dendrites. It's like mycelium, the underground network of fungus spreading through the forest floor. The universe has structure on the largest scales imaginable. But why? What created the structure? What carved out these voids and drew the galaxies together into filaments? The answer, once again, is dark matter. Let's go back. Way back. To the beginning. It's 380,000 years after the Big Bang. The universe has cooled enough that atoms can finally form, electrons binding to nuclei, creating hydrogen and helium. For the first time, light can travel freely through space. The universe becomes transparent. This moment, called recombination, leaves an imprint that we can still detect today. It's called the cosmic microwave background radiation, the faint afterglow of the Big Bang, visible in every direction we look. When we map this radiation with extreme precision, we see something beautiful. The universe at 380,000 years old wasn't perfectly smooth. There were tiny variations in temperature, hot spots and cold spots, differing by only 1 part in 100,000. These tiny variations were the seeds of everything that would come later. Here's what happened. In regions that were slightly denser than average, gravity pulled more strongly. Matter started to accumulate. These regions grew denser still, pulling in more matter, growing more massive. But this process, this gravitational collapse, happened primarily with dark matter. Remember, dark matter doesn't interact with light or normal matter except through gravity. It could start collapsing immediately, while normal matter was still being pushed around by radiation pressure. Dark matter fell together first, creating gravitational wells, invisible structures that normal matter would later fall into. Over hundreds of millions of years, the dark matter formed a scaffolding, a framework, the cosmic web. And into this web, like water flowing into a mold, normal matter flowed. Hydrogen and helium gas fell into the dark matter halos, compressed, heated up, and began to form stars. The galaxies we see, the bright, shining collections of stars, are tracing the invisible structure of dark matter beneath them. They're foam on the waves, candles marking the presence of something we cannot see. The cosmic web is a web of darkness. The light is just decoration. Now let's think about those voids, those enormous empty regions between the filaments of the cosmic web. When I say empty, I mean almost empty. There are a few galaxies in these voids, sparse, isolated, separated by vast distances. But mostly there's just space. Dark space. Space expanding, carrying those few galaxies farther and farther apart. Imagine being on a planet orbiting a star in a galaxy in one of these voids. When you look up at your night sky, you see almost nothing. A handful of faint smudges, galaxies millions of light years away, no Milky Way band stretching across your sky, no thousands of visible stars. Just darkness and silence and an emptiness that stretches in every direction farther than the human mind can truly comprehend. It's lonely. It's the loneliest place imaginable. A civilization arising there might never know that the universe is filled with galaxies. They might think they're alone, truly alone, the only island of light in an infinite ocean of darkness. But here's what's strange. What's beautiful in its own way. Those voids aren't truly empty either. They contain dark matter, just much less of it than the filaments. They contain dark energy, that mysterious force causing the universe's expansion to accelerate. And they contain a few stray atoms of hydrogen, drifting alone through space. And they contain something else. Something that connects them to the filaments, to the galaxies, to us. They contain the past. Light from distant galaxies travels through these voids, crossing them over millions or billions of years. The void is filled with ancient light, photons that began their journey when the universe was young, carrying information about stars and galaxies that may no longer exist. The darkness is full of memory, full of history, full of stories told in light so old as it might as well be archaeological. In 2008, a team of astronomers announced something puzzling. They had been studying the motion of galaxy clusters, measuring not just their motion relative to their neighbors, but their motion relative to the cosmic microwave background, the reference frame of the universe itself. They found that hundreds of galaxy clusters across a huge swath of sky were all moving in the same direction, flowing as if pulled by something enormous beyond our observable horizon. They called it the dark flow. If real, and the evidence remains controversial, it suggests something profound. It suggests that there's structure in the universe beyond what we can see, beyond the observable universe. Regions so distant that light from them hasn't had time to reach us yet in the 13.8 billion years since the Big Bang. We might be swimming in an ocean of darkness so vast that our entire observable universe, all 93 billion light-years of it, is just a drop, a bubble, a local region in something infinitely larger. This is where we run up against the limits of what we can know. The observable universe has a horizon, a boundary beyond which we simply cannot see. Light from beyond that horizon hasn't reached us yet, and because the universe is expanding, might never reach us. There could be an infinity of galaxies beyond our horizon. There could be regions with completely different properties, different laws of physics even, if some theories are correct. There could be other observers, looking up at their own sky, seeing their own cosmic web, their own darkness between their own lights. We don't know. We can't know. The darkness beyond our horizon is impenetrable, not because it's opaque, but because the universe itself prevents the information from reaching us. It's the ultimate darkness, not the darkness of matter that doesn't emit light, not the darkness of a black hole's event horizon, but the darkness of cosmic causality itself, the boundary between what can affect us and what cannot. We need to talk about something that might be the strangest thing in all of science, something that makes dark matter look simple by comparison. Dark energy. In 1998, two teams of astronomers were studying distant supernovae, exploding stars that we can use as standard candles to measure cosmic distances. They were trying to measure how fast the universe's expansion is slowing down due to gravity. Except they found that the universe's expansion isn't slowing down. It's speeding up. This shouldn't be possible. Gravity is attractive. Everything in the universe is pulling on everything else. The expansion should be slowing, like a ball thrown into the air, gradually losing speed as gravity pulls it back down. But instead, it's as if the ball is accelerating upward, as if there's an anti-gravity force pushing everything apart, growing stronger as the universe expands. This force, this dark energy, makes up about 68% of the universe's total energy density. Dark matter makes up about 27%. Normal matter, stars, planets, gas, dust, everything we can see, everything we're made of, makes up less than 5%. We are the minority. We are the exception. We are living in a universe that's composed primarily of things we don't understand. Dark energy is even more mysterious than dark matter. At least with dark matter, we know it behaves like matter. It clumps together due to gravity, it forms structures, it sits in definable places. Dark energy is different. It's spread evenly throughout space. It doesn't clump. It doesn't vary. It's a property of space itself, a kind of repulsive force inherent in the vacuum. Some physicists think it might be related to something called the cosmological constant, a term Einstein added to his equations and later called his biggest blunder. He added it to keep the universe static before we knew the universe was expanding. Now it turns out something very much like his cosmological constant might be real after all. Other physicists think dark energy might be a new type of field, a quintessence field that fills the universe and changes over time. Still others propose even more exotic ideas: modified gravity, extra dimensions, quantum effects from virtual particles in the vacuum. We don't know. And what's more troubling, the amount of dark energy we observe is incredibly small compared to what quantum field theory predicts. The prediction is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the worst prediction in the history of physics. Something is deeply wrong with our understanding of reality. Let's follow the dark energy into the future. Let's see where this leads. Right now, the universe is 13.8 billion years old. Galaxies are still forming stars. The Milky Way and Andromeda are on a collision course. They'll merge in about 4 billion years, creating a giant elliptical galaxy that astronomers have nicknamed Milkomeda. But as time goes on,
As dark energy continues to push space apart, the universe will change. Distant galaxies will move away from us faster and faster. Eventually, they'll be receding faster than the speed of light, not moving through space faster than light, which is impossible, but carried away by the expansion of space itself. These galaxies will disappear. Their light will be stretched to wavelengths so long that it becomes undetectable. They'll cross our cosmic horizon and vanish from our observable universe forever. In 100 billion years, an observer in Milkomeda will look up at the night sky and see almost nothing. A few satellite galaxies slowly falling in to merge with our own. But beyond that, darkness, empty space, an infinite void. They'll look out and see no evidence of the Big Bang, no distant galaxies receding, no expansion. They'll see a static universe containing one galaxy surrounded by eternal darkness. Will they figure out the truth? Will they understand that they're living in an old, dispersed, expanded universe? Or will they think this is all there ever was? The universe is becoming lonelier. The expansion, driven by dark energy, is isolating galaxy clusters from each other. Eventually, only gravitationally bound structures, galaxy clusters and their superclusters, will remain visible to each other. Everything else will be carried beyond the cosmic horizon.
Let's keep going, far into the future now. Stars will continue to form from the available gas in galaxies, but that gas is finite. Eventually, it will be used up. In a trillion years, a time scale so long that the current age of the universe is a tiny fraction of it, star formation will cease. The last stars will flicker and die. Red dwarfs, the smallest and longest-lived stars, will burn for tens of trillions of years, but eventually, even they will exhaust their fuel and fade. The universe will go dark. Not the darkness of matter that doesn't emit light, but true darkness, the absence of any light at all. What will remain? Black holes. Slowly evaporating through a process called Hawking radiation, so slowly that a solar mass black hole takes 10 to the power of 67 years to evaporate. Supermassive black holes, like Sagittarius A star, will take 10 to the power of 100 years or more. But eventually, even they will vanish. And what's left? Darkness. Pure, complete darkness. A universe filled with nothing but low-energy particles spread so thin that they'll almost never interact with each other. A universe that has reached maximum entropy, complete disorder, where no energy can be extracted to do work, where nothing can happen. Physicists call this the heat death, the final state of the universe, the end of everything. It's a cold, dark future, a universe that began in brilliant light and inconceivable heat, ending in frozen darkness and absolute silence. But here's what's beautiful, in a strange way. We're here now, in the bright time, in the era when stars are forming and galaxies are colliding and life is possible. We're living in the universe's youth. It's springtime, before the long winter sets in. We're like flowers blooming briefly in a garden, before the season changes and everything goes dormant. But for now, for this brief cosmic moment, we get to exist, to think, to wonder, to look up at the darkness and try to understand it. Let me take you somewhere else now, somewhere closer to home. It's late evening in a small town somewhere on Earth, the kind of town that still has dark skies, far from the light pollution of cities. You're walking down a dirt road, leaving behind the last streetlight, venturing into the darkness. At first, it's uncomfortable. Your eyes haven't adjusted. You can barely see the road beneath your feet. There's a primitive part of your brain that's screaming warnings.
Darkness means danger. Darkness means predators. Darkness means the unknown. But you keep walking. And slowly, slowly, your eyes adjust. The stars emerge. First the bright ones, Sirius, Vega, Arcturus, then fainter ones, then fainter still. After 20 minutes, your eyes have reached their full sensitivity, and the sky has transformed. The Milky Way stretches overhead like a river of light. Not a simple band, but a complex tapestry of bright and dark regions, clusters and voids, the entire structure of our galaxy visible to your naked eye. You can see dark nebulae, those clouds of dust that block the light of stars behind them. The Great Rift running through Cygnus, the Coalsack Nebula in the Southern Cross. These aren't absences, you realize. They're presences. They're material. They're places where stars are being born. The darkness is creative. The darkness is fertile. The darkness is necessary. Pause. For most of human history, this is what every night was like. Every culture on Earth grew up with these stars, this darkness, this perspective. The sky was a constant companion, a calendar, a storybook, a source of wonder and terror and meaning. But now, more than 80% of the world's population lives under light-polluted skies. In most cities, you can only see a handful of the brightest stars. The Milky Way is completely invisible. An entire generation is growing up never having seen the full glory of the night sky. We're losing our relationship with darkness. We're losing our connection to the cosmos. We're losing part of what makes us human. Let's think about why we can see stars at all, why our eyes are sensitive to light from objects trillions of miles away. Eyes, all eyes, from the simple light-sensitive spots of flatworms to the complex cameras of octopi to the remarkable instruments in your own skull, evolved to detect light. But why? What advantage does vision provide? In the earliest days of life on Earth, simple organisms evolved patches of cells sensitive to light. This allowed them to tell up from down, light from dark. They could swim toward the surface where photosynthesis could occur, or hide in shadows to avoid predators. Over hundreds of millions of years, these light-sensitive patches became more sophisticated. They developed lenses to focus light, muscles to adjust those lenses, neural processing to interpret the patterns of light and dark. But here's what's remarkable. Eyes evolved primarily to see things close by, to find food, to avoid danger, to navigate the environment. The fact that we can also use our eyes to see stars, to collect photons that have traveled for years or centuries or millennia through space, is almost an accident. A beautiful, improbable accident.
There's something magical about dark adaptation, the process by which your eyes adjust to darkness, becoming exponentially more sensitive over time. When you first enter darkness, you can see almost nothing. Your pupils dilate, opening wide to let in more light. But that's just the first step. In your retinas, you have two types of light-sensitive cells. Cones, which detect color and work best in bright light, and rods, which detect only black and white, but are far more sensitive. In bright light, your cones are active, and your rods are saturated, flooded with light, unable to distinguish any more detail. But in darkness, the opposite happens. Your cones become useless, but your rods begin to wake up. There's a chemical in your rod cells called rhodopsin, visual purple, that breaks down in light and regenerates in darkness. As you sit in darkness, your rod cells fill up with rhodopsin, becoming more and more sensitive. After about 30 minutes, your eyes have reached their maximum sensitivity. You're now about 100,000 times more sensitive to light than you were in bright daylight. This is why astronomers use red lights. Red light doesn't break down rhodopsin as quickly as white or blue light. You can preserve your dark adaptation while still being able to see your surroundings. There's something meditative about the process, about sitting in darkness, waiting patiently for your eyes to adjust, for the invisible to become visible. It requires patience, stillness, trust. It's a lesson, maybe, for how we should approach mystery in general, not with harsh light and demand for immediate answers, but with patience, allowing our perception to adjust, waiting for the hidden to reveal itself. Every culture that has looked up at the night sky has created stories about what they see, constellations, patterns in the stars, but they've also created stories about the darkness, about those dark patches in the Milky Way, about the voids between the stars. The indigenous Australians saw in the dark patches not absence, but presence. They saw the emu in the sky, a constellation made not of stars, but of darkness. The dark nebulae formed the body of an emu, stretching across the Milky Way. To them, the darkness was just as important as the light, just as meaningful. It wasn't empty space to be ignored. It was part of the story, part of the pattern, part of the meaning. In South America, the Inca had similar dark constellations: the llama, the fox, the toad, all made from the dark patches in the Milky Way. They recognized that these dark regions moved with the stars, were part of the celestial sphere, had their own significance. Even in Western astronomy, we give names to the darkness: the coal sack, the Pipe Nebula, Barnard 68, a dark nebula so dense that it blocks all visible light from stars behind it, appearing as a black hole in the sky, though it's nothing like an actual black hole. What are we really doing when we name the darkness? We're making it familiar. We're making it less frightening. We're asserting that it has a place in our cosmos, in our understanding, in our story. Names are powerful. They transform the unknown into the known, the terrifying into the manageable, the infinite into something we can hold in our minds. But naming also has limits. Some things resist naming. Some darknesses are too vast, too strange, too fundamental to fit into our categories. Dark matter, dark energy, these aren't really names, they're placeholders. They're admission of ignorance dressed up in scientific terminology. We're saying, there's something here, something real, something important, but we don't know what it is. Let's be honest about something. Darkness frightens us. It always has. We evolved as diurnal creatures, active during the day, vulnerable at night. In darkness, our primary sense, vision, becomes nearly useless. Predators have the advantage. Dangers are hidden. The familiar becomes strange. Children are afraid of the dark. They see monsters in shadows, imagine threats in every creak and rustle. We tell them there's nothing to fear, that it's just darkness, but part of us remembers that fear never entirely goes away. It retreats into the background, but it's still there. As adults, we've learned to manage this fear. We've created artificial light, banishing darkness from our homes and streets. We've explored the darkness, mapped it, explained it. We know that shadows don't contain monsters, but cosmic darkness, that's different. That's a darkness so vast and deep that no amount of light can fully illuminate it. A darkness that contains things, dark matter, dark energy, black holes, that challenge our understanding of reality itself. This darkness doesn't threaten us physically. The dark matter passing through your body right now isn't going to hurt you.
Black holes are light years away and will never reach Earth. Dark energy might eventually tear the universe apart, but not for trillions of years. No, this darkness threatens something else. It threatens our sense of understanding, our feeling of control, our belief that the universe is, fundamentally, knowable. There's a philosophical concept called horror cosmicus, cosmic horror. The idea that the universe is so vast, so strange, so indifferent to human concerns that merely understanding it properly would drive us mad. That there are truths too large and terrible for the human mind to bear. The writer H.P. Lovecraft built an entire literary career on this concept. His stories are filled with ancient cosmic entities, beings so powerful and so alien that humans who encounter them go insane from the revelation. But I don't think that's quite right. I don't think cosmic darkness drives us mad. I think it does something else. I think it humbles us. It puts us in our place. It reminds us that we're small, temporary, contingent, but also that we're part of something larger. That we're embedded in a cosmos that existed long before us and will exist long after us. And there's something comforting in that, strange as it sounds. We're not the center. We're not the point. The universe doesn't revolve around us, and that means we can relax a little, let go a little, accept our limitations.
Here's a thought that might seem contradictory. Darkness creates the conditions for light. Think about stars. Stars are born in darkness, in those thick clouds of gas and dust that block visible light. The darkness provides shelter, allowing the gas to cool and condense. Gravity pulls the material together, compressing it, heating it, until nuclear fusion ignites and a star is born. Without darkness, without those dense molecular clouds, stars couldn't form. Light requires darkness as its birthplace. Think about eyes. In a world of constant bright light, there would be no advantage to having sensitive eyes. It's the existence of darkness, of night, of shadows, that made eyes worth evolving. Darkness created the need for light detection. Think about consciousness itself. We sleep. We dream. We require darkness and rest to process information, consolidate memories, maintain our mental health. Constant wakefulness, constant light would destroy us. We need the darkness. Even in physics, there's a principle called the Pauli exclusion principle that says no two fermions, particles like electrons, can occupy the same quantum state. This creates the structure of atoms. This gives matter its solidity, its distinctness. In a sense, this is a kind of darkness, a fundamental rule that says not everything can be in the light at once. There must be separation. There must be boundaries. Without this principle, all matter would collapse into the same state. There would be no structure, no complexity, no us. Darkness, in the form of boundaries, limits, the impossibility of perfect transparency, makes existence possible. Let's come back to you. Yes, you listening to this right now. You're made of atoms that were forged in the hearts of stars. Carbon, oxygen, nitrogen, iron, all the heavy elements in your body were created by nuclear fusion in stars that lived and died billions of years ago. When those stars exploded as supernova, they scattered these elements into space, into dark clouds of gas and dust. And in those dark clouds, a new generation of stars formed, our sun. And around our sun, planets condensed from that same dark material. Earth, our home, made of darkness, forged in darkness, gestated in darkness before emerging into light. And on this planet, in the ocean, in the darkness of deep water, life began. Simple chemicals organizing themselves into increasingly complex patterns, metabolism, replication, evolution. For most of Earth's history, life existed only in darkness, in the ocean depths, in the microbial mats, in places where sunlight couldn't penetrate. Only later did life emerge into the light, develop photosynthesis, colonize the surface. You carry this history in your body. Your cells still function best at body temperature, in darkness. Your DNA replicates in the darkness of the cell nucleus. Your thoughts, those electrical patterns firing across neurons, exist in the darkness of your skull, never directly exposed to light. You are, in a very real sense, a creature of darkness. Your consciousness emerges from darkness. Your memories are stored in darkness. Your dreams play out in darkness. And when you look up at the night sky, you're not just looking at something external. You're looking at your origin. You're looking at where you came from. You're looking at what you're made of. The darkness above and the darkness within, they're connected. They're the same darkness seen from different perspectives. Let's think about the future now, about how we're trying to understand the darkness, to find dark matter, to explain dark energy. Deep underground, beneath mountains in Italy and South Dakota in China, detectors sit in the dark, waiting. They're surrounded by tanks of liquid xenon or crystals of germanium cooled to near absolute zero, shielded from cosmic rays and radioactive contamination. They're waiting for a dark matter particle to collide with an atom. Just one collision, one signal that would prove dark matter exists as particles and give us a clue to what those particles are. Scientists have been waiting for decades, building larger detectors, refining techniques, reducing backgrounds, analyzing data. So far, nothing. The darkness keeps its secrets. In space, telescopes are searching for dark matter in other ways. The Fermi Gamma Ray Space Telescope looks for gamma rays that might be produced when dark matter particles collide and annihilate. The Euclid telescope, launched in 2023, is mapping the distribution of dark matter by measuring how it bends light from distant galaxies. On the ground, the Large Hadron Collider smashes protons together at nearly the speed of light, trying to create dark matter particles in the lab. If dark matter particles can be created, their presence would be inferred from missing energy, energy that goes into particles we can't detect. We're hunting the darkness with every tool we have, with ever more sensitive detectors, with ever more powerful telescopes, with ever more sophisticated theories. But there's a possibility, a humbling, frustrating possibility, that dark matter might not be made of particles at all. It might be something else. Black holes from the early universe, modifications to the laws of gravity, quantum effects we don't understand. Or it might be particles, but particles so weakly interacting that we'll never detect them directly. We might be forced to study dark matter only through its gravitational effects, forever denied the satisfaction of catching one in a detector. The darkness might remain dark forever.
Dark energy is even more mysterious than dark matter. With dark matter, we at least have a clear observational signature. Galaxies rotate faster than they should. Gravitational lensing shows mass where there are no visible stars. We know it's there, even if we don't know what it is. Dark energy is different. We know the universe's expansion is accelerating. We can measure this acceleration.
But we don't really know if it's caused by something, some substance or field, or if it's just a property of space itself, something built into the fabric of the universe at the most fundamental level. Some physicists think dark energy might vary over time. Maybe it will get stronger or weaker as the universe ages. Maybe it will reverse, turning from repulsive to attractive, causing the universe to collapse back in on itself in a big crunch. Others think it's constant, the cosmological constant that Einstein proposed and rejected. A property of the vacuum that never changes, that will continue pushing the universe apart faster and faster, forever. Still others propose that we're misunderstanding something fundamental, that dark energy is a signal that our theory of gravity, general relativity, breaks down on cosmic scales, that we need new physics, new equations, new ways of thinking about space and time. What's unsettling about dark energy is its fine-tuning. The amount of dark energy in the universe seems carefully calibrated. If it were much stronger, the universe would have expanded so fast that galaxies and stars could never form. If it were much weaker, or attractive instead of repulsive, the universe might have recollapsed early on. We exist in a universe where dark energy is just right for complexity to emerge, for stars and planets and life. Is this coincidence? Design? Are there multiple universes with different amounts of dark energy, and we necessarily find ourselves in one where conditions allow our existence, a kind of cosmic selection effect? These are questions that take us to the boundary between physics and philosophy, questions that might not have scientific answers at all. But let's not be too pessimistic. We're living in a golden age of astronomy. New instruments are coming online that will transform our understanding of the dark universe. The James Webb Space Telescope, launched in 2021, can see deeper into the universe than ever before. It observes in infrared light, which can penetrate dust clouds and reveal objects too distant or too cool to see in visible light. It's showing us the first galaxies, born just a few 100 million years after the Big Bang, emerging from the cosmic dark ages. The Vera Rubin Observatory, named after the astronomer who proved dark matter exists, will begin operations in 2025. It will photograph the entire visible sky every few nights, creating a movie of the changing universe. It will discover millions of asteroids, supernovae, variable stars, and it will map the distribution of dark matter throughout the universe with unprecedented precision. Gravitational wave detectors like LIGO have opened an entirely new way of observing the universe. They detect ripples in space-time itself, created by colliding black holes or neutron stars. These waves travel through darkness, unimpeded by gas or dust, carrying information about the most extreme events in the cosmos. Future detectors, LISA, a space-based gravitational wave observatory, the Extremely Large Telescope, a 39-meter optical telescope being built in Chile, the Square Kilometer Array, a radio telescope that will span continents, will push our senses even farther. We're extending our eyes, building new eyes that can see in wavelengths we evolved no sensitivity to. Eyes that can detect phenomena we never imagined existed. And with these eyes, we're exploring the darkness, not just the darkness of space, but the darkness of our understanding, the unknown. Every answer raises new questions. Every discovery reveals new mysteries. The darkness recedes, but it never disappears. There's always more to explore, more to understand, more to wonder at.